see if it works.
Nah, yeah, I guess. Bro, look at what? Oh, on your sorry. Look at us. It's a drop on me. That's my sister. That's Antoine.
Get any for me?
Antoine has such nice curls.
Get any for me?
You guys all have nice curls.
You got a bag for me, right? Come on. No?
Hey, look at Antoine now. I don't know. Post is about me every time. So last night I studied flashcards with your daughter in a month. Okay, or just got a few things to put aside and went in the room and studied. Like, what? Where's the whole stuff? I think it's deleted everything.
Thank you. Thanks for that the thumbs up back there. I see. All right, thank you. So what we're going to talk about now is something called summation or graded potentials, and then we're going to be ended up talking about how do action potentials activate things and how do they behave. And one of the things that I wanted to tell you is sort of equivalent to the contraction of a sarcomere. So a sarcomere contracts. If this is the length of a sarcomere, it contracts all the way, or it doesn't contract at all. Similarly, action potentials or neurons behave in the same way. They either send the signal all the way or they don't send it at all. So then how do you send a stronger signal? And that's important because you can't modify the strength of the signal at all. What I'll tell you in a little bit is that you modify the frequency of the signal. You don't modify the strength of the signal. But before we get to that point, we're going to talk about how do you start sending these signals. And when we're talking about neurons communicating here, we see a little bit of this synapse right here. We see the dendrite that on the right-hand side, this is the dendrite receiving through exocytosis these chemicals that are crossing the synaptic cleft right here. That's what we're going to be talking about on Monday. So for right now, once again, if this action potential gets generated right here at the axon hillock, it comes all the way down here, and then it stops right here and nothing happens. It's as if that thing never happened. That signal never got sent. So the only way that that signal can be responded to in this picture right here is to cross this synaptic cleft and then to propagate that action potential to the right. Right? It doesn't happen any other way. It can't happen. And if it doesn't happen, then it's as if you're ignoring some information. The first thing we want to talk about here is in terms of action potentials. They're called graded potentials. And graded potentials are represented in a relatively small change in the membrane potential. And that membrane potential might go from -70 to -60. And again, now I'm going up, right? So remember, I'm using negative numbers here. So that the membrane potential goes up here. If you have a number of small points on changes in the membrane, right? Those number of small changes can sum or can add to, and then result in reaching a threshold. If they reach that threshold, then that action potential gets propagated. If they don't reach a threshold, once again, then it's ignored. In terms of graded potentials here, graded potentials can happen from a number of different things here, including mechanical and temperature signals, ligands, again, are chemicals here, and then changes across the plasma membrane, again, electrochemical changes, right? So those are, we've talked about those already. So let's just talk about how in this picture right here in the upper right-hand corner, we have a couple of numbers here. So 1, 2, and 3 represent the influx or the import of sodium into the cytosol of the soma. Okay, so not the axon right here. So this is import of sodium into the soma. And if you look at if just a little bit of sodium goes into the cell, then there's just a slight depolarization. If there's a little bit more and a little bit more, then there's those things will add up. And so if you look at this depolarization, this number 1 here accounts matches up with the those numbers right here. So as you go from left to right on this graph right here, the depolarization increases in level. And as they increase in level, they sum. And once they reach a certain level, again, that threshold, once they reach that threshold, then it can get propagated. So that summation means that that adjacent small signals can get added to one another. But it can also be that if there's too much time between the signals, then the signals can disappear. So if there's a second or a subsequent depolarization, signals that are not that are too far in the recent past, right, too far away, then those things, that first depolarization signal will disappear. So that means, why is that disappearing? Again, because of the structure of the neuron is continually trying to maintain that's negative 70 millivolts so that it's ready to send that action potential when needed. If you talk about a couple of different ions and you look at this, see, these are some characteristics of gradient potentials, the title is. Let's just look at a couple of ions, in particular sodium, potassium, and chloride. Those 3 ions will increase the permeability of the plasma membrane, and if they increase the permeability, then it increases the movement of those ions in a diffusive manner, in other words, down the concentration gradient, and as a result of that movement, the resting membrane potential gets modified. That increased permeability there, again, gets modified. And those gradient potentials can, again, sum, or summate, it's called here. So several stimuli that wouldn't be enough to cause an action potential can get added together and then produce an action potential. And these neurons, when they're triggered there, these gradient potentials will send signals down the axon there, and we already talked about the phases of the action potential. That is to say, depolarization, repolarization, hyperpolarization. I'm not going to use this term after potential, and return to the resting membrane potential. So resting potential or resting membrane potential, I also abbreviated RMP, resting membrane potential. That's what that is right there. Now, the trick here is that regardless of whether it's a very strong signal or a series of very, very small signals that are summed and they exceed the threshold, regardless of how you reach that threshold, the neuron will send that signal in an all or none principle, just like the sarcomere will contract in all or none. That all or none principle says that an action potential occurs, and it occurs as long as it exceeds that threshold. Here in the book, or in my notes right here, I write down it's negative 55 millivolts. I'm not going to ask you to remember that. I'm just going to say it's greater than the threshold. So these action potentials here, so these characteristics of action potentials, once they reach that threshold, they send that signal in all or nothing principle here. As a result of that all or nothing principle being sent there, the depolarization causes the permeability of sodium to change, and then repolarization causes the permeability of potassium to change. When I say permeability here, I'm talking about the permeability, the ability of the sodium or the potassium to move across that axolemma, and as a result, that's caused by these channels either opening or closing. So the permeability is a response to the 2 things. The first is there's a concentration gradient across that phospholipid bilayer, and the second is those channels are opening. And those channels are specific to either sodium or potassium or chloride or calcium. There's a period of time when the neuron doesn't respond. It's unable to respond, and that's called a refractory period. And that refractory period is when basically when the sodium potassium pump is reestablishing itself. The strength of the stimulus here, the stimulus strength, determines the frequency of action potentials. Action potentials don't change in the strength. So a muscle contraction can change in its strength, but an individual sarcomere contraction cannot. Okay, so an individual sarcomere contracts a certain distance, and it's dictated by the length of the proteins in the sarcomere. The strength of the action potential is dictated by the charge across that phospholipid bilayer, that axolemma, and it can't get any stronger. So again, here's this classic graph of resting membrane potential, depolarization, repolarization, hyperpolarization. During this time, where my pointer is right here, during this time, all the way to this time, there's something called a refractory period. So you can't do something again if you're doing something right now. It sort of sounds silly, but that's what this is saying. I'm jumping the gun here. So here, let me just bring this up, and I'll go back to this a second. So this refractory period means that while the action potential is getting sent, while the resting membrane potential is changed, while the depolarization and repolarization and hyperpolarization is happening, the depolarization, it passed that threshold, the depolarization, repolarization, hyperpolarization. During that time, there's a refractory period, and that area of the neuron can't send an action potential again because it's already sending it right now. So Tanya was just drinking her drink. Can she drink another drink while she's drinking a drink? Right? That doesn't make sense, right? And that's what this is saying. Okay? So you can't send another action potential while you're sending the action potential. You can't set that action potential until you're established this resting membrane potential. And once again, look at the time here on the x-axis here. This is in milliseconds. We're talking about 1 or 2 milliseconds. We're not talking about a very, very long period of time. So let me back up here. And again, we'll just talk about these. We talked about ligand-gated ion channels here. Let's talk a little bit about voltage-gated ion channels. How are they, what are the ions going to do, and how are they going to do? So first of all, look on the left-hand side here. We have phospholipid bilayer with these. Now this, I will use this term as a phospholipid bilayer. I would then call this an axolemma. The axolemma is a very, very highly specific phospholipid bilayer, and that's important. There are more potassium inside the cell than outside the cell, so there's more sodium outside the cell than inside the cell. And the first thing that happens is the voltage activates the red gates, and those red gates are permeable to sodium. So the voltage causes, when the red gates open and it exceeds the threshold here, and either by summation or the insult is great enough, those red gates open, and then that occurs. After that, the purple gates open, and that's what's illustrated. So here is the depolarization. The sodium gates are open. The depolarization is happening here. There will be some leak channels opening, but these things are minor in comparison. This diffusion into the cell occurs dramatically. As repolarization happens, then the inactivation of the sodium ion channels occurs, and the activation of the potassium ion channels occurs. That activation of the potassium ion channels only occurs after the sodium channels have been activated. So it never happened before, and it doesn't happen, it only happens as a result of that. We talked about the movement of sodium potassium here, and if there's too much sodium moving out, potassium moving out, and too much chloride moving in, then you get hyperpolarization, and that hyperpolarization Chloride is not illustrated in this drawing right here, but potassium is, and that's where we're seeing right here. And once again, I'm not going to talk about this idea of after potential. It's going to be hyperpolarization. So that brings us to refractory period here. This refractory period means that no matter how frequent this summation occurs, right, it's not going to happen again. It's doing something, it's in the middle of doing something, and it's not going to send it again. I don't distinguish between absolute and relative refractory period, but I just distinguish between, the concept here of refractory period is generally what I'm talking about. So if you look at the bottom of this graph right here, this general refractory period is what I would ask about. So now how do you get increased strength of a signal? And so that's this last message for today. So you don't increase the strength of the action potential, you only increase the frequency. If you, the number of potentials produced per unit of time, so in other words, how frequent are they? If it's in a second, do you do 1 per second or 10 per second? That second instance here, that signal is 10 times stronger, and that signal then will be response. If it's a muscle, if it's a gland, whatever it is, that whatever is responding there is going to get, the signal is going to be 10 times stronger. If you're at a threshold or subthreshold stimulus, there's no response. Threshold stimulus is defined as something that is just enough to cause an action potential. Submaximal stimulus is, again, it's equivalent to a threshold stimulus. And then I don't distinguish between maximal and supramaximal. Maximal stimulus causes a maximum frequency of action potentials here. So the way that we talk about action potentials here is either subthreshold, there's no action potential. Threshold, there's an action potential. Increased numbers is submaximal, and then maximal, you can't get any faster. Why can't you get any faster? Because of the refractory period. You can't fit any more in there because it's just too much, there's not enough time. Yes?
When it comes to reflexes, right, like great fast reflexes, would that be like maximal?
So what you're talking about here is a very, very rapid response to an impetus or to a signal, right? And this is talking about increasing the strength of something over a period of time. So you can have an automatic response. I've told that story about someone throwing an orange at me and I went like this and I caught it, right? So there's a learned reflex. If you're at a doctor's office and you hit is this a tendon or a ligament? At my patella.
Ligament.
It's a ligament, right? You hit the patellar tendon, patellar ligament rather, and you hit it, and then the quadriceps tendon will stretch, and then it'll cause your leg to contract. That happens that's not as a result of summation or anything like that. That's just an example of this whole process happening. So the initial stimulus, so you're at the doctor's office, you get hit with the patellar tendon or the patellar hammer. That gets up, and we're going to talk about that. I don't know if it's in this. It might be in the next chapter, or we're going to talk about reflexes later on this semester. But it goes from the signal, it goes up to the central nervous system, and it comes right back down. Some of them bypass the central nervous system, go right back down to the muscle, and it causes the muscle to respond. So that's just an illustration of how fast it can respond. Okay? What this is talking about is how do you increase the strength of a response. If you look at this picture right here, these are on the bottom. These are the strength of the signals here. So on the left-hand side, you have submaximal threshold or a single threshold. You barely reach the threshold, and as a result of barely reaching this threshold, now this line right here is that first graph that I showed today, where you have the resting memory potential is negative 70 millivolts. It goes up to about positive 30 or 35. It goes back down to 90, and it goes back up. So that entire graph is right where my pointer is. So that's just sending a single action potential. If you get it, you increase it a little bit, you can double that rate or triple that rate. At some point, you can't increase that anymore. So this is exceeding threshold. This is the sub-maximal threshold, these two. This is the maximal threshold. And if you look at these last two are not any different. Why not? Because there's a refractory period between these action potentials, and there's a time which the body has to wait. It's not very long, but that time that the body has to wait as a result of that, it can't respond. And by the way over here on the left, what type of action potential am I illustrating right over here, where my pointer is? None. Why is that? Because the signal is less than the threshold, and so as a result of that signal being less than the threshold, there's no response. So regardless of whether you have a single response or as many responses as you can, those responses don't increase in magnitude, they increase in frequency. That frequency is dictated by the strength of the response, but that frequency has a limit, and that limit is dictated by the refractory period. Okay? And that's what this is saying right here. So it's not a larger magnitude right here, but just an increased frequency. This all or nothing, all or none principle, all or nothing principle doesn't produce weak action potentials. It produces the same level of action potential, the same strength of an action potential, and regardless of the strength of the signal, as long as that signal exceeds threshold. And let's see here. I think what we're going to do is stop right here. And so we're going to stop right here. And first thing is, let's see here. It's 9:56. I'm going to text Miss Binninger in a couple of minutes.